Greetings everyone. Today we're going to be talking about the second law of thermodynamics. As you recall, the first law dealt with energy conservation, and so that was the internal energy of the system is equal to the heat added to the system plus the work that's done on the system. So if we just take, for example, a pendulum, and this pendulum is going to be swinging back and forth, it has some internal energy. Over time, we know that this pendulum would stop swinging, and so this pendulum is going to be just stopped, and then heat is added to the world or the room or whatever. And so the energy is conserved, but this internal energy was converted into heat. But there's no reason, according to the first law, that we couldn't go this way. Start with a stopped pendulum, take heat from the room, and then start the pendulum swinging again. According to the first law, this is perfectly valid. But the second law forbids this. The second law also tells us why heat goes from hot things to cold things. And it also is going to explain some bigger consequences to the universe. And we'll talk about each of these things. So let's point out some observations that we have that deal with the second law. The first is that heat flows from a high temperature reservoir to a cold temperature reservoir. And then that makes the temperature between these two equal to each other. So we notice that if you set a glass of ice water out, that the ice will melt. But if you set a glass of water in the room, ice will never spontaneously form. So another one is that no heat engine can convert work with 100% energy, with 100% efficiency. Some of the energy is exhausted as heat. So we'll talk about heat engines in the next slide. The next one is that no refrigerator can move heat from a cold region to a high region without the input of work. So this deals with these first two. One is that there's no perfectly efficient heat engine, and the next one is that this is not that moving from cold to hot is not spontaneous. And the last one is that entropy always increases for some isolated system. So the way that we can visualize a heat engine is that we have some hot reservoir, we have some cold temperature reservoir, and we're going to take heat from the hot reservoir, do some thermodynamic process, and then we're going to do some work from this engine, and then we need to exhaust some amount of heat to the cold temperature reservoir. So the energy flow goes from hot, and then it outputs into work and outputs into the exhaust. And so that's written by QH is equal to work plus QC. So if you want to know how efficient this thing is, you want to say, what is the work that's being done, and then divide it by how much energy you input. So for this guy, our efficiency would be the work over QH. And so we can rewrite this in terms of QC. We can rearrange this guy and then get 1 minus QC over QH. So we can do the same thing for a refrigerator. A refrigerator is basically just a heat engine run in reverse. We're doing work to be able to pull heat from a cold temperature reservoir, like the inside of your refrigerator, and dump it into a hot temperature reservoir, like your kitchen. And so the energy flow goes from work plus QC, that's this side, is equal to QH. And then we can talk about the efficiency of a refrigerator, but a lot of times you'll hear this coefficient of performance for the cooling or for the heating, and that's going to be just QC over the work. And so we can rewrite this in terms of just the Q's here. So if you remember that the efficiency is equal to the work that's being done over QH. So if you have a 100% efficient engine, then all of the work is equal to the the Q in, and we're not dumping any heat into this cold temperature reservoir. So what you could do, if this were possible, is hook this guy up to your refrigerator, and then now this would look like TH, and then we're just bringing a smaller amount of heat up, right? And then TC. So this part of the cycle, and maybe a little bit of this, would collapse itself, and then you would just bringing cold heat from the cold reservoir into the hot reservoir. So basically you would generate a refrigerator that would work for free. And this is not valid due to the second law. So you actually can't have an engine that's 100% efficient. And it's actually worse than that. You can't even do better than a Carnot engine. A Carnot engine, so the efficiency is the exhaust over the absorbed. But a Carnot engine has an efficiency that we can relate in terms easier than just Q. We can actually talk about it in terms of the temperatures. So let's just say that your temperature was 250 Kelvin was your cold reservoir and 500 Kelvin was your hot temperature reservoir. So then your efficiency is going to be 1 minus that. So it's going to be 0.5 or 50%. So you actually can't make an engine that will operate more efficiently than 50% if you have it set between these two temperature reservoirs. The reason why the Carnot engine is the most efficient is because there's no change in entropy in this system. If we look here, we have an isothermal expansion. So then we're getting Q added to the system. Then we do an adiabatic compression expansion, and so that means that Q is 0. Then we do an isothermal compression, and this is Q out, and then we do another adiabatic compression. So these two adiabatics, Q is 0, and we know that the change in entropy is going to be this, basically the heat exchanged over the temperature. So for these adiabatic, we are not changing the entropy of the system. And for these isothermal, this Q and the Q in and the Q out are equal to each other. So we basically we add entropy to the system one time, and then we subtract entropy from the system at the other step. So the net change in entropy for the Carnot engine is 0. This is why it's the most efficient. If you did some other process, then the net entropy of the cycle would not be 0. The problem with the Carnot engine is that we have these two isothermals, and isothermals can only happen if it's infinitely slow. And so no real engine will ever have these isothermal expansions or compressions. These are just idealizations. So you will never make an engine that's more efficient than this Carnot engine. Just to wrap up the laws of thermodynamics, the first law was energy is conserved, so your E thermal is equal to your heat plus the work. The second law dealt with entropy, and it says that the entropy of the system is equal to the change in the heat that you add or subtract from the system over the temperature that occurs at. So this has some consequences. One is that you can't convert heat completely to work, and the other one is that the direction of heat flow, that heat goes from hot to cold. The third law just basically says that only a perfect crystal at absolute zero has zero entropy, basically. But the consequences for this are that you can't reach absolute zero. No matter how good of a refrigerator you make, you can't reach absolute zero. You can only get closer and closer and closer. It'll take an infinite number of steps for you to be able to get there. So there was the Ginsburg theorem, which is kind of a comedic way of looking at these laws of thermodynamics, which is the first law is that you can't win. So if you put heat in, you can't get more work out than you put heat in. And then you can't break even, which is that you can't make something 100% efficient no matter what you do. And then the third one is that you can't even get out of the game. Some of the consequences for the second law are that you can't make any machine that's going to have perpetual motion. So if it was just the first law, then you could have a pendulum basically that could just swing back and forth until the end of time. But because of the second law, we know that any of these processes are going to dump some amount of heat out. And when you dump heat out, you're changing the entropy. And when you change entropy, that process is no longer reversible. And so then you can't pull heat back out of the system and make this pendulum swing. So you will never create some perpetual motion machine. The other consequence is because of this irreversibility of processes that we know the direction of time. So the first law doesn't say anything about which way time should flow in some process. But because of the second law and because we know that systems grow in disorder, in entropy, then there are some processes, or most processes, are irreversible. And these lead to disorder of the system that keeps increasing. Basically, we know that the delta S of the system has to be greater than or equal to 0, where only this equal to mark deals with reversible processes. And the only reversible processes are either isothermals that are infinitely slow or adiabatic expansions or compressions. Other kinds of processes are going to lead to increase of entropy of your system. So the other one is that you can't use energy at 100%. We just talked about this. Basically, you can't even beat the Carnot engine, which is this. And since you can't go down to absolute 0, this fraction will always be significant. These all lead to what we call the heat death of the universe, which are basically, since heat flows from hot to cold, then eventually everything will be at the same temperature. And then when you get everything at the same temperature, then now you can't make any kind of engines. Basically, this efficiency goes to 0. You can't pump heat from one place to another because everything has the same temperature. And so then if you can't pump heat around, then you can't do any work. And if you can't do any work, then how can you sustain life? Here's a problem for us. So a heat engine takes in some amount of thermal energy, and then it's going to do this at a reservoir that's at 500 K. And then we want to return some of this energy. So if we draw out this, we're going to have something at 500 K. Up here, we're going to bring some amount of heat energy, do some process on it, dump some out into a cold temperature reservoir, but we don't know what this is, basically. And then we're going to do some amount of work. So if this engine operates at an efficiency of 0.41, then what is the biggest that we can make TC? So our efficiency is 1 minus TC over TH. This is kind of our upper bound, so we're going to assume that this is a Carnot engine. And then we can solve this for TC. So I'm going to bring eta over to this side and TC over TH over to this side. And then multiply both sides by TH. So I'm going to get TC is equal to 1 minus eta times TH. So now I can just plug in what I know. So 1 minus 0.41, then times TH, which is 500 Kelvin. So then my TC is going to be 295 Kelvin. We have a certain coal-fired power plant that's going to generate some amount of electric power. So this is our work, is 600 megawatts. The plant uses some amount of coal each day, and that coal can produce some amount of energy per kilogram. So this is our heat energy. So QH is then going to be the amount of coal that we have, 3.3 times 10 to the 7th joules per kilogram. And then we're going to multiply this by 4.8 times 10 to the 6 kilograms by the amount of coal that we have. So then QH is this product. The steam that drives the turbines is at a temperature of 300 Celsius. So that's our TH right there. 300 Celsius, which is 300 plus 273, which is 573 Kelvin. Our cold temperature reservoir is then going to be at 37 degrees Celsius plus 273 is going to be 310 Kelvin. So then our Carnot efficiency is going to be 1 minus Tc over Th, which is 1 minus 310 over 573, which is going to be 0.46. So then our real efficiency is going to be the work that's done all over our QH. So the work that's done is 600 megawatts, so that's times 10 to the 6th watts. And then per day, so we have 24 hours in a day, times 60 minutes, times 60 seconds. And then all this is going to be divided by our QH, which is 1.58 times 10 to the 14 joules. And all this is going to give you about 0.33. So about 33% efficiency actual, whereas our Carnot efficiency was about 0.46. So we're always going to be less than this Carnot efficiency. So what is the thermal energy that we exhaust each day? So we can take this efficiency, and that's equal to the work over QH, which is equal to 1 minus QC over QH, and then rearrange this to be 1 minus eta equals QC over QH, and then solve for QC. So this is going to be QH 1 minus eta. And then this is going to give you about 10 to the 14 joules of heat are being dumped into the water. So this is why power plants often use a big lake as the cold temperature reservoir, because we have to get rid of a lot of heat. Last problem is going to deal with a refrigerator. This refrigerator has a coefficient of performance of 3.8. So that means that the Q that we're exhausting, that we're pulling in, the last problem we're going to deal with is with a refrigerator. This refrigerator has a coefficient of performance of 3.8, which is going to be equal to our QC over the work that's done. But here we have power, and power is equal to work over time. So this is our unit of power, is 200 watts. So this is basically saying that there's 200 joules per second. So this is the work, this is the power that's being done, which is like the work that's being done per second. So then we can get basically the power of the QC, how fast heat is being pulled out of the freezer. And then that is going to be like, we're just going to multiply this work up here and then divide by seconds, which is going to give us a power. So this would be like 3.8 times the work that's being done, and then we're going to divide that by seconds. So this is like 3.8 times the power, which is going to be 3.8 times 200 watts, which is 760 watts. So now we want to know how long it's going to take to freeze an ice cube tray that has 600 grams. So this is our Q of the ice that we need to freeze, and that's MLF. So this is 0.600 kilograms, then times 333,000 joules per kilogram. So then we want to know how long this is going to take. So then we take this power of the heat being pulled out, So this is PQC, which is equal to Q, basically C over the time. And we want to solve for this time. So then this time is going to be equal to QC divided by the power QC. So this is equal to the 0.60 kilograms times this 333,000 joules all over this 760 watts. So then this T is equal to 260 seconds. So now we can ask, what's the change in entropy of the ice and of the kitchen? So delta S of the ice is going to be equal to the Q of the ice all over the temperature. The temperature is not zero. All these temperatures need to be in Kelvin. So this is equal to minus ml over, there's a kb down here too, kb times 273. And what you're going to get is about minus 5.3 times 10 to the 25th joules per Kelvin. Sounds like a big number, but that's because of this kb and that we have like basically a mole of water molecules sitting here. So now what about the kitchen? And that's going to be the Q out of the whole thing. And it's not going to be equal to the same thing because Q out is not equal to the Q ice because our refrigerator isn't 100% perfect. So the Q out is equal to the Q in plus the work that's done all over this kBT. So both of these are equal to 0.6. So that's basically the Q of the ice times this 333,000. And then now plus the work that's being done, which is 200 watts of power times 260 seconds. And then all divided by kBT. And this is also at, we're also dumping this out at 270, 22 degrees Celsius, so we need to add on to 273 Kelvin. And this will give you 6.2 times 10 to the 25th joules per Kelvin. And the first thing that you'll notice is that this number is bigger than this number. So delta S of the kitchen is greater than delta S of the ice, which means that our delta S of the system is greater than 0.